Last module discussed universal service and internet working and how a physical network used routers for interconnection. We also covered internet architecture and virtual networks. Now we will discuss routers and routing in more detail. During this module, we will discuss the structure of a network that spans an arbitrarily large area and describe the basic components used to build a packet switching system. We will also cover dynamic routing and explain the fundamental concept of routing by presenting the two basic routing protocols, link state routing and distance vector routing, and cover the advantages of each and their use on the internet. Networking technologies can be classified according to the distance spanned. PAN spans a region near an individual, and LAN spans an entire office or building. A MAN or CAN spans a large metropolitan area, and a WAN spans multiple cities or countries. However, the factors other than distance are taken into consideration. Consider a company that uses a satellite bridge to connect LANs at two sites. Should the network be classified as a WAN or as an extended LAN? The key issue that separates WAN technologies from LAN technologies is scalability. A WAN must be able to grow as needed to connect many sites and spread across large geographic distances. A technology is not classified as a WAN unless it can deliver reasonable performance for a large-scale network. So a WAN does not merely connect many computers at many sites. It must provide sufficient capacity to permit all computers to communicate. Thus, a satellite bridge that connects a pair of PCs and printers is merely an extended LAN. Let's look at traditional WAN architecture. Designers of the traditional WAN chose to create a special purpose hardware device that could be placed at each site. Called a packet switch, it provides local connections for computers at the site as well as connections for data circuits that lead to other sites. A packet switch consists of a small computer system with a processor, memory, and I/O devices used to send and receive packets. Early packet switches were constructed from conventional computers. However, the packet switches used in the highest speed WANs require special purpose hardware. The internal architecture of a packet switch is illustrated in this figure. The first WAN was created by the U.S. Air Force in the late 1950s to interconnect sites in the semi-automatic ground environment radar defense system. It was an enormous network of dedicated phone lines, telephones, and modems linked the sites together. Therefore, keep in mind that the traditional WAN creation was before the LAN. Wide area networks were in use to allow computers to connect before personal computers were even developed. Since the advent of LAN technology, most WANs separate a packet switch into two parts. A layer 2 switch that connects local computers, and a layer 3 router that connects to other sites. The figure illustrates the separation. This architecture allows communication with local computers to be separated from transmission across a WAN. A WAN can be formed by interconnecting a set of sites. The exact details of the interconnections depend on the data rate needed, distance spanned, and the delay that can be tolerated. Many WANs use leased data circuits, but microwave and satellite channels are available. A network designer must choose topology for any given set of sites, and many topologies are possible. Topology is the physical makeup. Remember a few modules ago we talked about bus, star, mesh, partial mesh, ring, and it describes how and which sites are connected together. The figure illustrates a possible way to interconnect. As you can see, a WAN does not need to be symmetric in interconnections among packet switches, and the capacity of each connection can be chosen to accommodate expected traffic and to provide redundancy. The goal of a WAN is to allow as many computers as possible to send packets simultaneously. The fundamental paradigm used to achieve simultaneous transmission is known as store and forward. To perform store and forward processing, a packet switch buffers packets in memory. The store operation occurs when a packet arrives. Input-output hardware in the switch places a copy of the packet in memory. The forward operation occurs once a packet has arrived and is waiting in memory. The processor examines the packet, determines its destination by looking at the destination IP address, and sends the packet over the I/O interface that leads to the destination. A packet switch, or router, is a layer 3 device that reads instructions found in the layer 3 header to see how to process the packet. In this case, it can view the destination address. Unlike a MAC address, the source and destination address does not change in transport across the internet. From the view of an attached computer, a traditional WAN network operates similar to a LAN. Each WAN technology defines the exact frame format a device uses when sending and receiving data, and each device connected to a WAN is assigned an address. Addressing in a WAN follows a key concept that is used in the internet: hierarchical addressing. Hierarchical addressing divides each address into two parts: the site and the computer at the site. In practice, instead of identifying a site, each packet switch assigned a unique number with the first part of an address identifies a packet switch and the second part identifies a specific computer. You can compare this addressing scheme to house addresses and street addresses using a 5-digit zip code that specifies the post office and the 9-digit zip code, the last 4 digits, that specify a location. The figure shows each address as a pair of decimal integers. The computer connects to port 5 on packet switch 1 and is assigned the address 15. In practice, an address is represented as a single binary value with some bits of the binary value used to represent a packet switch and the remaining bits to identify a computer. Internet addresses consist of a binary number where the prefix bits identify a specific network in internet, and the remainder bits identify a computer attached to that network. What is the importance of hierarchical addressing? When a packet arrives, a switch must choose an outgoing path to forward that packet. If a packet is destined for a local computer, the switch sends the packet directly to the computer. If the destination is not the local packet switch, the packet must be forwarded to another packet switch. To choose, a packet switch examines the destination address in the packet and extracts the packet switch number. If destination address is identical to packet switch's ID, the packet is intended for a computer on the local packet switch. Otherwise, the packet is intended for a computer on another packet switch. The algorithm explains this computing. The packet switch does not need to keep complete information about how to reach all possible computers, nor does a packet switch need to compute the entire route a packet will follow. Instead, a packet switch bases forwarding on packet switch IDs and only needs to know which outgoing link. In other words, a switch only needs to compute the next hop for a packet. This process is called Nexthop forwarding and is analogous to the way airlines list flights. To make the computation efficient, packet switches use table lookup. Each packet switch contains a forwarding table that lists all possible packet switches and gives next hop for each. Compare to a mail carrier who picks up a letter from a mailbox. He or she then takes it to the post office regardless of the final destination. The letter gets forwarded to a distribution center as the next hop. Each time the letter is forwarded, it gets closer to its final destination. Originally, forwarding tables were called routing tables. The figure illustrates next hop forwarding with a trivial example. Using only one part of a two-part hierarchical address to forward a packet has two practical consequences. First, the computation time required to forward a packet is reduced because the forwarding table can be organized as an array that uses indexing instead of searching. Second, the forwarding table contains one entry per packet switch instead of one entry per destination computer. The reduction in table size can be substantial, especially for large WAN that has many computers attached to each packet switch. A two-part hierarchical addressing scheme allows packet switches to use only the first part of the destination address until the packet reaches the final switch. Once the packet reaches the final switch, the packet switch uses the second part of the address to choose a specific computer. Next hop forwarding does not depend on the packet's original source, nor on the path the packet has taken before it arrives at a particular packet switch. Instead, the next hop to which the packet is sent depends only on the packet's destination. The concept is known as source independence. Source independence allows the forwarding mechanism in a computer network to be compact and efficient. When all packets follow the same path, only one table is required, plus forwarding then does not use source information. Only the destination address needs to be extracted from a packet. A single mechanism handles forwarding packets consistently whether the packet originates on directly connected computer or if the packet arrived from other packet switches. Packet source does not matter. An example would be the route a plane travels does not depend upon where passengers began their journey. A forwarding table must guarantee universal communication, and the forwarding table must contain a valid next hop route for each possible destination address. The forwarding table must contain optimal routes for a destination. Thus, in the forwarding table, the next hop value for a given destination must point to the shortest path to the destination. Network failures further complicate forwarding. For example, if two paths exist to a given destination and one of the paths becomes unavailable because hardware fails, forwarding should be changed to avoid the unavailable path. A network manager cannot merely configure a forwarding table to contain static values that do not change. Instead, software running on the packet switches continually tests for failures and reconfigures the forwarding tables automatically. We use the term routing software to describe software that automatically reconfigures or updates forwarding tables. Route computation in a WAN can be compared to a graph that models the network, and the routing software uses the graph to compute the shortest path to all possible destinations. Each node in the graph corresponds to a packet switch in the network. Note that all individual computers are not part of the graph. If the network contains a direct connection between a pair of packet switches, the graph contains an edge or link between the corresponding nodes. The figure shows an example of a wide area network and the corresponding graph.